Okay, there we go. Uh, okay, so I guess we're still just doing. So we're still doing conditional probability. Let's remind ourselves about that just real quick. So well, the real definition is probability of A given B. So this is the probability of A given B. The math definition or whatever is that this should be the probability of A and B over the probability of B. But really what it means is just like, since you're given B, it's like, okay, assume B is true, then find the probability of A. So what it really means is assuming B happens, what's the probability A happens? Right. So we did a lot of this on Friday. And let me just tell you one more word that we talked about quite a bit on Friday, since several of us weren't here. Yeah. All right. The last thing is independence. Which, I mean, it is what it sounds like. If two things are independent, they shouldn't affect one another, right? So if the probability of A given B is the same as the probability of A, so nothing changed when I told you B definitely happens, then A and B are independent. Otherwise, they're dependent. And the main example of independent is, we're going to talk about this a lot when we get to the statistics part of this and out of the probability part. Yeah, don't. You're not supposed to come late, so okay, I guess that's fine. But yeah, next time when the door shuts, it's shut. So. The main example is repeated trials. So if you do the same thing over and over again, like if I draw a card from a deck, put it back, draw it again, put it back, draw it again, all those are independent of each other. So, okay. So let's go back to the problem. It says, after having sonogram, the pregnant woman learns she will have twins. What's the probability she will have identical twins? All right. Which I guess they didn't give us whatever else. So we know we're having twins. Yeah, let's just open Excel. Wow. So waiting to get it. Okay, we don't need to open it. Okay, we can. Okay. So out of all those possibilities, which ones are identical twins? This is a whole lot easier than it sounds. So it's just the identical twins row, right? So those guys right there are all identical twins. Right? So that's the number of ways I can get identical twins, and then twins in general would be anybody that's actually in this table. So So it's 18 out of 50 or 0.36. So, a simplified fraction. So 18 out of 50 is 9 out of 25. Okay, after saying it more closely, the physician says, hey, we're going to have twin boys. Now what's the probability they have identical twins? So this is where the conditional part comes in. I mean, before we were looking at all twins, so it's kind of no big deal. But here, now we know it's boy, boy, so we're definitely in this first column. So if I know I'm in the first column, what's the probability I have, or she has identical twins? 9 out of what? Yeah, 17, but yeah. All right. So there's 9 ways she can have identicals. 9 and 8 is 17 ways she can have boy-boy twins. Right? Or I guess I should say, there's 9 ways she can have boy-boy identicals, and then 17 ways she can have boy-boy twins. All right. Let's go with about 35. So is anybody rooting for the Broncos? One person very adamantly, one person kind of. So everybody congratulate Miss Boy. She's a huge Broncos fan. Of course, apparently the game started out really bad. She said she quit watching it, but then she's like, when she found out they won, it's like, okay, I have to go back and watch it. All right. To recruit slab before cost for one samples from that, or okay, further testing is done only if the combined samples is positive. Based on past results, there's 0.1 probability of finding bacteria in a public swimming area. Find the probability that a combined sample from the 3 areas will reveal the presence of bacteria. Is the probability low enough that further testing is rarely necessary? Okay. So let's write it out. It's pretty simple. So we've got 3 guys. Each one, I mean, the probability of the first guy is 0.01. The probability of the second guy is 0.01. The probability of the third guy is 0.01, right? Okay. But what we're saying is that we're going to combine them together. So we want the probability A or B or C, right? And we said that, well, when you do probabilities of or, you would think you just add them together. But there's a problem because if like either A or B, if A and B both happen, then you counted it when you did probability of A, and you counted it again when you did probability of B. So you have to subtract off like probability of A and B. So again, this is the bad way to go about it. We're going to do this the good way here in a second. But the bad way to go about this would be to say, okay, if I want A or B or C, I could have A, I could have B, or I could have C, right? But I just double counted if I have both A and B, right? I also double counted if I have both B and C. And I also double counted if I have A and C, right? Well, what if I have all 3 of them? If I have A, B, and C, well, I counted it 1, 2, 3 times, but I took it away when I did A and B. I took it away again when I did B and C. I took it away again when I did A and C. So I counted it 3 times, but I took it away 3 times. So I really haven't counted it at all yet, right? So I would have to add back in A and B and C. Actually, it's not that hard to do it this way, so let's do that. But so that's if you have three things. If you have four, it's the same thing. You add all the odd numbers of choices, and you subtract all the even numbers of choices, however many you have. So if you wanted to do it this way, well, A, B, and C are all 0.1s, right? If I do A and B, well, these two pools are independent of each other. So when I do probability of both of them, I just multiply them together. So what's 0.01 times 0.01? Well, let's just say 0.01 squared. And those two are the same. So minus 0.01 squared, minus 0.01 squared. And then the same thing, since they're all independent, this is just 0.01 to the third. So all together, wow, somebody's really excited in the next room. So I've got 3 times 0.01 minus 3 times 0.01 squared plus 0.01 cubed, which is that. So again, that's kind of the long way to do it, but just so that you've seen it, that is one way you could go about it. The other thing we could have done instead, okay, it was 0.00297 or whatever. So the other thing we could have done that would have been a little faster, we're looking for the probability of A or B or C, right? Well, A or B or C is the same thing as not. This is kind of funny to write down, not A and not B and not C. Okay, we'll sit here and think about what that says. So if I want to say that at least one out of A, B, and C is true, that's the same thing as saying, okay, not A and not B and not C are all false, right? Does that make any sense at all? Okay. Well, yeah. I mean, the point is, the main thing is, okay, if I want to say A is true, that's the same thing as saying not A is false, right? That one's simple enough. The tricky part is if you want to say that ORs are, when you do not on the ORs, they turn into ands. Like if I want to say, hey, either Ty or Catherine went to Amarillo yesterday. Well, for that to be true, then, if for that to be false, then Ty had to have not gone to Amarillo and Catherine had to not go to Amarillo. So when you negate an or, you get ands. Is the main point. So if I want to say A or B or C, well, if I want to be sneaky and think, well, what would the opposite be? It would be not A and not B and not C. And this probability is easy to find because we said when you do the probability of nots, it just is 1 minus, right? Because probably something happens and it doesn't happen. Well, they have to add up to 100. So this would be 1 minus the probability of not A and not B and not C, which the probability A didn't happen is 0.99, and they're independent. So when we do the ands, it's really easy. It's just 0.99 times 0.99 times 0.99. So the other thing we could have done was just 1 minus, and I'm sure what MathXL was actually wanting you to do, If my pen would start writing, there we go. 1 minus 0.99 cubed, right? Because the probability that any one test negative is 0.99. The probability all 3 tests negative is 0.99 cubed. So the probability at least one of them tests positive is 1 minus that. Right? So if I go back to Excel, let's just check, make sure this really does work. 1 minus 0.99 cubed. Yeah, sorry. 0.99 cubed. Sure enough, we got the same thing. So that's a little bit easier. But I kind of wanted you to see both. So is that probability pretty low? Yeah, I'm putting the 3 together still makes it basically, well, anything less than 5% is pretty low. So so it will be rarely necessary. And it will be necessary sometimes. Cool. Let's go about 3. So. This is homework 3. So I try to stay about a week ahead, which I guess I'm actually, well, no, because homework 2 is due tomorrow. So we're really not just terribly far ahead. We're like maybe 1 day ahead or something. But basically, I like to have homework 3 finished by the time you're supposed to start it. So I guess we're really not ahead, because if I finish it today, then, well, you'll finish up homework 2 tomorrow and then start homework 3 before Wednesday. Because y'all all start homework 3 as soon as you finish homework 2, don't you? All right. Thank you, Annie. I knew somebody did. All right. So this guy, we actually talked about this, but we hadn't done anything with it. So let me remind you. There's kind of 3 things. Well, there's really 2 things left in this homework we haven't done yet. So one is permutations and combinations. We talked about a little bit on Wednesday. Actually, let's restart the